I'll ask the next presenter, that's Inés Llopart from SCK-CEN, and she's going to talk about chlorine 36 and iodine 129 in decommissioning samples. So we stay on tough analysis and tough samples. The floor is yours. Thank you very much.
Thank you very much. So I will share my screen first. Can you see it properly?
Yeah, perfect.
Wait. So, yeah. Let's see if it works. Yeah. So, hello everyone. I am Inés Llopart, a PhD student from the Belgian Nuclear Research Center. First of all, I would like to thank the opportunity to present my project on this group meeting. So today I would like to talk about the determination of chlorine 36 and iodine 129 in nuclear solid decommissioning samples, and mainly focusing on our big challenge, that is chlorine 36 memory effect and how to deal with it. So here you have all the points that I would like to go through the presentation. And initially, I would like to briefly introduce the field of research. So once a nuclear facility arrives to the decommissioning phase, then large amounts of materials are created and need to be characterized in order to assess the correspondence to the acceptance criteria. Depending on the radiological risk of waste, the materials can be released in the environment in an unconditional or conditional way, or in case that they are considered radioactive waste, they must be disposed in a near surface disposal or deep geological disposal, depending on the activity concentration. So once these materials are sorted, then a dose impact study is performed in order to meet the specifications for all the end solutions. Therefore, materials need to be nuclide specific characterized in order to comply with the legislation requirements. So for radiological waste characterization, different type of analysis can be performed. On the one hand, non-destructive analysis allow a direct measurement from the outside of the waste package, and that's the reason why they are called easy to measure. Mainly gamma ray emitters are measured by this type of analysis. And on the other hand, destructive analysis need a sample treatment before the measurement, and that's the reason why they are called difficult to measure. In this case, mainly alpha and beta particle emitters are measured by this technique. So nowadays, scaling factors are used to correlate the activity of difficult to measure radionuclides with the activity of gamma emitters, such as cobalt-60 or cesium-137. These factors are used in calculation codes that are validated via real analysis. However, the main issue is the high uncertainty on the inventory of difficult to measure radionuclides. So this project is mainly focused on two difficult to measure radionuclides, chlorine 36 and iodine 129. Both radionuclides are significant for final waste disposal because of their long half-lives and the high environmental mobility. So on one side, chlorine 36 is coming from the neutron activation of natural occurring chlorine 35. It is a high beta emitter, and it's mainly present in construction materials as trace element and in the primary circuit column. On the other side, fission iodine 129 is a fission product of uranium-235. It is a low beta emitter, and it's mainly present in spent nuclear fuel and in the primary cooling circuit of a nuclear reactor. So as mentioned, both are beta emitters. So as you can see on the spectra below, in case that they are both present with other potential interferences, and spectral overlapping could occur. Hence, the aim of this study is optimizing the quantification of chlorine 36 and iodine 129 in solid samples coming from the decommissioning activities. The main issues nowadays are the high uncertainties on the inventory of these difficult to measure radionuclides, the high detection limits, the high turnaround time of the full procedures, and the high amount of chemicals needed. So the further application of this optimized procedure would be for improving the radiological characterization, reaching low limits of detection in order to comply with the clearance levels on the legislation, and including this procedure in routine analysis. So the experimental setup could be explained in 3 steps. First of all, the solid sample combustion using a pyrolyzer. Then we went through the radiochemical separation using chlorine resin cartridges. And then at the end, the measurement technique would be liquid scintillation counting. So the pyrolyzer for the combustion step, a pyrolyzer from Radec was used, adapting the procedure from Warwick's presentation in 2010. Different parameters were tested, such as temperature protocols depending on the type of matrix. A maximum temperature of 900 degrees was established in order to stimulate fully chlorine release. A flow rate of 200 milliliters minute was used in order to carry all the gases and volatile elements through the tube. No catalyst and neither quartz beds were used in order to regulate the flow rate into the trapping solution. And glass connections and quartz tubes and sample boats were used in order to avoid any chlorine sticked on the plastic surfaces. Chlorine and iodine carriers were used for quantifying the chemical recovery and were added at the beginning of the procedure on the solid sample. And blanks were always run after each active sample in order to evaluate possible effects. So the second step, the radiochemical separation, was based on Zulaw's publication in 2010 also, and where a solid phase extraction was performed using chlorine resin cartridges together with a vacuum box in order to speed up the procedure. So the figure that you have on your right is showing the radiochemical separation procedure, where chlorine was eluted with ammonium thiocyanate and iodine was eluted with sodium sulfate. So as mentioned before, because both are beta emitters, and in case of potential interferences such as tritium or carbon-14, a spectral overlapping could occur, and that's the reason why we did the radiochemical separation. So for the sample measurement, the massic activity was calculated based on liquid scintillation counting measurements, and we used a low-level liquid scintillation counter. The samples were prepared mixing the elution medium together with 50 milliliters of liquid scintillation cocktail. The massic activity was calculated following the formula below, where the CPS were taken from the liquid scintillation counting measurements. The chemical recoveries were calculated based on stable measurements, ion chromatography for stable chlorine, and inductively coupled plasma mass spectrometry for stable iodine. And at the end, the counting efficiency was calculated using quench curves. So for the optimization of the procedure, the different steps were investigated, evaluating different type of parameters. So for the combustion step, we tested the temperature protocol, holding time at 900 degrees, the amount of sample, and then we also tested the possible memory effect of the target radionuclides. For the separation step, we tested the compatibility with different media for loading the solution into the resin, and then we also took into account the cleaning steps in order to remove the potential interferences. And for the measurement, we did the calibration in order to quantify the counting efficiency, and we also took into account the homogeneity and stability of the samples to measure. So during the optimization of the procedure, we found an issue with chlorine-36 contamination in the blanks. However, it was not the case for iodine-129. So how to deal with this chlorine-36 memory effect? Initially, we hypothesized that could be a cross-contamination effect on the vacuum box, and that's why we tested blanks together with spike samples on the same vacuum box, and then we compared these results with blanks run in a different vacuum box. There were no significant differences on the blanks, meaning that there was no cross-contamination effect. And then we tested the possible chlorine-36 memory effect spiking samples with chlorine-36 tracer and then running blanks afterwards. We confirmed this chlorine-36 memory effect, and then we went to look for the reason or the possible parameters that were influencing this chlorine-36 memory effect. That in our case, we hypothesized that were quartz bull and quartz beds, moisture, bubblers, or sample boats. So for quartz bull, once we saw the contamination, we remove it from the, and quartz beds also, we removed them from the setup itself. And then as you can see, the contamination was slightly decreasing. Then we spike a sample and we ran another blank. And as you can see, the contamination was back again, meaning that it was not possible to completely remove this chlorine-36 memory effect. But even that, we calculated the chemical recoveries in order to see if it was really needed to use these quartz bull and quartz beds on the setup. And as you can see on the squares below, there were no significant differences on the chemical recoveries, meaning that we could remove them from the setup. We proceed on the same way with the moisture. So once we saw contamination, then we remove the moisturizer, that in our case was water, on the setup, and then we saw that the contamination was not either increasing neither decreasing, and that's why we spiked sample and we saw that the contamination was increasing. So we conclude that moisture was not really affecting the chlorine-36 memory effect. Anyhow, we also quantify the chemical recoveries in order to see if it was really needed to use the moisturizer on the setup. And as you can see on the squares below, there were no significant differences on the chemical recoveries, meaning that we could also remove the moisturizer from the system. For the bubblers, once we saw contamination, then we changed them for new bubblers. And then as you can see, the contamination was gone. Then we spike a sample, reusing the new bubblers, and then we saw contamination back. We changed the bubblers for new ones again, and then we saw that the contamination was decreasing, but it was not possible to completely remove this chlorine-36 signal. So even changing the bubblers for new ones. And for the sample boats, we proceed on the same way as the bubblers. Once we saw contamination, we changed the sample boats for new ones, and then we saw that the contamination was over. We spike a sample, and then we ran another blank, and we saw that the contamination was slightly increasing. And once we switched with new sample boats again, we saw that the chlorine-36 memory effect was decreasing, but still it was there. So it was not possible to completely remove this effect. Another parameter that we tested, it was the aging of the sample boats, because in the literature it was reported that the quartz structure could suffer some variations while increasing the temperature. And here on the figure that you have of your left, with experimental points, we could prove that indeed there was a chlorine-36 memory effect related to the aging of the sample boats. So in our case, after 20 times reusing the same sample boat, the memory effect was significantly increasing. And we also calculated the chemical recoveries in order to see if there were significant differences between using a new sample boat and a reused one. And as you can see, the chemical recovery was higher while using a new sample boat. Another thing that we tested, it was adding cleaning steps after running its active sample. Initially, we tested cleaning with diluted nitric acid, and as you can see, the chlorine-36 memory effect was slightly decreasing. Then we also had a second cleaning step that was with ammonia 25% solution, and then the memory effect was decreasing again, but still it was there, so we could not completely remove this memory effect even with adding cleaning steps. So that's why the reason why we kept a reasonable background level between 8 and 13 CPMs of the blanks. Another thing that we tested, it was using a catalyst on the last zone of the pyrolyzer, because in the literature it's reported that depending on the matrix and on the target radionuclides, different reactions are needed. So in case to need a reduction, a nickel catalyst could be used. In case of needing a oxidation, copper oxide or platinum alumina could be used. And in case of acceleration of breakage bond, iron oxide could be used. In some other cases, the catalyst cannot be directly removed from the setup because it's already included there. And this is the case of horizontal split tube furnaces up to 1100 degrees. So what we saw is that after spiking a sample, then we saw a huge contamination on the blank. We removed the catalyst, that in our case it was copper oxide, and we saw that the contamination was gone. We spiked the sample and we saw that the chlorine 36 memory effect was slightly increasing, meaning that indeed it was not possible to remove this effect just removing the catalyst, but there was a huge difference between the chlorine 36 memory effect after removing the catalyst and before, like while having it on the setup. This chlorine 36 memory effect is not the first time that is mentioned. It was mentioned for AMS measurements, a long-term chlorine 36 memory effect. So the overview of all these tests was that moisture catalysts and quartz wool and quartz beds were somehow having an influence on a few influence on the chlorine 36 memory effect, even that they could be removed from the setup. In case of the bubblers, even if we switch for new ones, we could still see this chlorine 36 memory effect. So indeed, it had an influence. But for us, the conclusion was that the major contributor for this chlorine 36 memory effect were the sample boats. So the conclusion of this approach was that chlorine 36 memory effect is a random effect. We cannot completely remove it from the procedure, but we could somehow correct it. Once the procedure was optimized, then we went for the application of the method. So what we did, it was using blank concrete and graphite samples spiked with chlorine 36 and iodine 129 tracers. And what we did, it was comparing the massic activity spiked with the measured activity, massic measured activity. Taking into account the count rate of the sample, the counting efficiency, the chemical recovery, and the mass of the sample. So what we obtained is shown here on this graph. As you can see, within an uncertainty sigma 2, the results were comparable, the activity measured with the activity spiked. So for the last step was calculating the detection limits, and they were evaluated based on measurement of different blanks and calculated according to the ISO norm 11929. The parameters that we considered were the count rate of the blank, the counting time, the mass of the sample, the chemical recovery, and the counting efficiency, obtaining a value of detection limit of 25 millibecquerels gram for both radionuclides, chlorine 36 and iodine 129. Then what we did, it was comparing this value, this detection limit, with the activity concentration values for exemption available on the current basic safety standard directive. And what we could see is that the detection limit of chlorine 36 was enough to reach this activity concentration for exemption, but it was, however, it was not the case for iodine 129. And another thing that we did, it was considering this chlorine 36 memory effect with a higher background, obtaining a detection limit of 45 millibecquerels gram. And again, it was still enough to reach the exemption values established by the legislation. So now I'm coming to the conclusions. This optimized procedure could be applied for analyzing real samples. This procedure could reach the required limits by the legislation for chlorine 36, and catalyst was not needed in our setup, avoiding the potential issues with chlorine 36 memory effect. And at this point, it was important to point out that blanks were a must, were required after running each active sample in order to evaluate the possible chlorine 36 memory effect. So the further work on these two radionuclides is investigating the applicability to using plastic scintillating microspheres for determining chlorine 36, improving iodine quantification in order to be able to reach the limit required by the legislation. And then it's important also here to point out that interlaboratory comparisons and reference materials are missing nowadays, and we need them to validate the procedure and the methods. So now I would like to thank first of all of you for your attention, and also to thanks Angie for founding the project, and Brussels University and Denmark University for promoting also the PhD.
Thank you very much for the very nice presentation. The detective work, actually. I mean, there's a lot of detective work that you have been doing. Very thorough, ruling out where the problem is. Yeah, very, very good. Thank you. There's already first question. Okay, so from NASA. So he says that iodine 129 can be measured by high resolution gamma spec. Why is it considered to be difficult to measure radionuclide?
Please, can you repeat the question? I couldn't hear the first part.
So he's asking iodine 129 can be measured by high resolution gamma spec. Why is it considered to be difficult to measure radionuclide?
Actually, because it's also beta emitter, and at some point, because it's a volatile element, the crucial step for both volatile elements, chlorine and iodine, it's the first step, the sample combustion, where you need to trap it in order to be able to do any separation, and especially in case that there are interferences.
Yeah, and I think, I mean, you've shown the detection limit, the requested detection limit for the iodine. That's seriously low. I mean, to get to the 10 millibecquerel per gram, that's going to be quite tricky. Do you have what are you going to try? Can you increase the sample mass, or do you have to go for mass spectrometry, or what do you think you will tackle next?
Actually, yeah. Thank you for your question. And by the way, we were wondering to try either like another type of measurement technique that could reach lowest limit of detection, going for a higher amount of sample, or even trying to increase a bit the chemical recovery for iodine. And then maybe the trapping solution, changing the trapping solution could be also an option.
Yeah, I think sodium hydroxide is going to work quite fine for the iodine. I think the chlorine was usually the more tricky one, especially with terms of oxidation set. Okay, another question from Dave Free. So he says you have an issue with sample boats which are made of silica. The work tube is also made of silica. Do you have evaluated chlorine 36 bonding with silicium dioxide in the work tube itself? So is maybe the work tube actually one of the additional sources of the cross-contamination?
Yeah, I believe like the issue, especially with the sample boats, is that somehow it's stick somewhere that we actually don't know. So what we saw, it was experimental results that were always giving an issue of chlorine signal on the blanks. But we cannot really say where is the issue, especially on the sample boats. We somehow can understand that it's coming as a major contributor on the sample boats, but we are not really sure. And we are actually using quartz sample boats in order to ensure that there's no chlorine sticked on the surface. So actually, like the issue itself, we don't know it yet. We are still under investigations.
Okay, thank you very much. So are there any other questions at the moment? If not, again, thank you very much. And there's a I think there's
Yeah, I
some...
just want. I think my
Okay.
question wasn't. You can measure iodine 129 without disturbing a sample. Like if you got 1 kilogram of soil from there you have, okay, you just put it on detector and measure iodine 129 by measuring its gamma energy as 39 keV. So my question is why you bother going through all the radiochemical separation and measure iodine 129, where you can easily, like cesium 137, you can measure it. That was my question.
Yeah, thank you very much for your question. But actually, our main concern was determining both at the same time, like simultaneously. That's why we went to liquid scintillation counting, even if we knew that it could work in a worse way, and actually it's a destructive technique on this sense, because we were pretty interested also in chlorine. That's why we went through these steps instead of going just for gamma.
So rather, in other words, you did your procedure for chlorine 36, which at the same time extracted iodine 129.
Exactly.
Okay. But that, I think in your procedure, you're saying a gamma spec is a known, well, easy to measure. So from your classification, actually, iodine 129 wouldn't strictly fall into that.
I think it's by the majority of the laboratory, it's still considered as difficult to measure. As you said, the gamma energy is fairly low, and the amount of sample you need to get to the detection limits is fairly large.
Yeah.
So you will probably have to take care of self-absorption. So yeah, it's kind of a maybe not quite proper definition, but the majority of the laboratories would tend to classify as difficult to measure.
Yeah. I think we used to measure iodine 129 by radiochemical separation for Sellafield. And they were quite happy because we were getting very low detection limit. But after some time, they found by doing gamma spec would meet the requirement for free release. So it's a decision to be made by the community. If they want very low detection limit, you can go for separation. But if you're not, then you might get away with that, going through the hassle of radiochemical separation.
And I think that's really the case here. It needs to be fit for purpose, and the detection limit you've shown that's a tough one, even with the radiochemistry. So not much choice, I'm afraid. Yeah. So good luck on this one. Okay. So if there are no other questions, again, thank you very much to all the speakers. So there's a break now. Let's reconvene if that's okay for you at 3:05 UTC time. So see you back in about 14 minutes. Bye. Again, thank you very much for participating.